Let's look at the logistics of logarithms. We'll start with the familiar exponential form, b to the x equals y. When translated into logarithmic form, it looks like log base b of y equals x. The corresponding colors show where each piece is in exponential form and then how it translates to logarithmic form. To make sense of this further, let's look at some examples with numbers. The familiar 3 squared equals 9 as a logarithm is log base 3 of 9 equals 2. Another familiar example is 4 cubed equals 64. When written in logarithmic form, it's log base 4 of 64 equals 3. We can translate these equations in both directions. For example, log base 2 of 8 might be hard to see, but when you write it in exponential form, it's clear that 2 cubed equals 8. Therefore, log base 2 of 8 equals 3. Sometimes, in a book or for example problems, you'll see a logarithm written without a base. If there's no base written, we assume that it's log base 10. This is called the common logarithm. Now, all you have to do is practice. I would suggest copying down the following, maybe even color coding it, and using it as a reference as you do practice problems. It's important to learn both forms. Depending on the problem, you might need to use one, the other, or both. The problems on the first page make more sense in exponential form. But what happens when you have an example like 2 to the x equals 5? We know that 2 squared is 4 and 2 cubed is 8, so it has to be somewhere in the middle of 2 and 3. Without logarithms, we would have to guess and check to find the solution. An example like this is where logarithms come in handy. Let's write it in logarithmic form. Log base 2 of 5 equals x. Now at this point, you might be able to use a calculator to figure out what x is. Many calculators operate in base 10, and it's not easy to change the base. This is one reason we have something called the change of base theorem. Before we talk about the theorem itself, let's see where it comes from. Take the example that we started with at the top, 2 to the x equals 5, or log base 2 of 5 equals x. Now let's establish some variables. Let's assume log 2 equals c and log 5 equals d. Let's write our variables in exponential form. Log 2 equals c would be 10 to the c equals 2. On the other side, log 5 equals d would be 10 to the d equals 5. Notice that we now have equations equal to 2 and 5. Let's take our expressions and substitute them in place of 2 and 5 in our original equation. Then use the exponent power rules to simplify. The only way that the following statement could be true is if c times x equals d. Now, we can solve for x by dividing both sides by c. If we replace c and d with our original equivalent expressions, we've uncovered the change of base rule. In this example, the change of base rule states that log base 2 of 5 is equivalent to log 5 divided by log 2 with a common base of 10. In more general terms, any example, log base x of y equals log base b of y divided by log base b of x. Again, this is called the change of base theorem or the change of base rule. Let's look back at our specific example. If you actually type log 5 divided by log 2 into a calculator, you should get approximately 2.32. You should try this on your own now and see if you get the same result. To learn more about logarithms, check out the logarithm playlist.